Hello there and welcome to the Dreamy Science channel. I'm so glad you found your way here tonight. Maybe you've been gazing up at the stars, wondering about the worlds that orbit our sun. Or perhaps you simply need a gentle journey to help quiet your mind before sleep. Either way, you're exactly where you need to be. Tonight, we're staying close to home in our own solar system, exploring the quiet wonders that drift through space alongside Earth. Let your breathing slow, your shoulders relax, and your thoughts settle like dust on a distant moon. Because tonight, we're taking a peaceful voyage through our celestial neighborhood, from the scorching surface of Venus to the icy rings of Saturn, from tiny asteroids tumbling silently through space to moons that harbor hidden oceans beneath frozen shells. Some of what you hear may surprise you with its gentle beauty. Other facts might simply wash over you like a warm tide, soothing and soft. If these calm explorations help you unwind or give you a restful way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one peaceful soul at a time. But for now, just breathe deeply and let's begin our quiet drift through the solar system we call home. Venus spins backward compared to most other planets. While Earth and most planets in our solar system rotate in the same direction they orbit the Sun, Venus does something beautifully different. It spins backward, slowly and deliberately, like a dancer moving against the rhythm. This retrograde rotation means that on Venus, the Sun would rise in the west and set in the east, if you could see it through the thick, pearlescent clouds that wrap the planet like a soft blanket. Venus takes 243 Earth days to complete just one rotation, making its day longer than its year. This leisurely backward dance gives Venus a unique character among the planets, a gentle rebel spinning to its own quiet tempo in the cosmic waltz. Jupiter has a faint ring system that glimmers like whispered light. When we think of planetary rings, Saturn comes to mind with its magnificent, obvious bands of ice and rock. But Jupiter, too, wears rings around its mighty form. These rings are delicate and subtle, made of dust particles so fine they're almost invisible, like cosmic silk threads catching starlight. They were discovered only in 1979, hidden in plain sight, waiting patiently for the right angle of sunlight to reveal their gossamer presence. Jupiter's rings are divided into 4 main parts, each with its own quiet story. The dust that forms them likely comes from tiny meteoroids striking Jupiter's innermost moons, creating gentle cascades of particles that settle into these ethereal bands. From Earth, we cannot see them with the naked eye, but they're there, a secret crown of light adorning the giant planet. Mars has the largest volcano in the solar system, sleeping peacefully for millions of years. Rising from the rust-colored plains of Mars stands Olympus Mons, a volcanic mountain so vast it would dwarf anything on Earth. It stretches roughly the size of France and rises nearly 14 miles into the thin Martian sky, making it almost 3 times taller than Mount Everest. But this colossal peak is not a place of fire and fury. It has been dormant for millions of years, a gentle giant sleeping under the pale Martian sun. Its slopes are so gradual that if you were walking up its side, you might not even realize you were climbing a mountain until you looked back at how far you'd come. Olympus Mons formed over countless ages through layer upon layer of quiet lava flows, each one adding to its height like pages in an ancient book written in stone. Mercury experiences the most extreme temperature swings of any planet. Despite being the closest planet to the Sun, Mercury leads a life of dramatic contrasts that unfolds with serene predictability. During its long days, which last about 88 Earth days, temperatures on the Sun face and side can reach over 800 degrees Fahrenheit, hot enough to melt lead. But Mercury has no atmosphere to hold this heat, so when night falls, temperatures plummet to nearly 300 degrees below zero. This means that on Mercury, you could theoretically find both scorching desert and frozen wasteland just a few hundred miles apart. The planet's surface is covered in ancient craters, silent witnesses to billions of years of impacts, creating a landscape that looks like a peaceful, airless moon frozen in time. Saturn's rings are made almost entirely of water ice. Those magnificent rings that make Saturn one of the most beautiful sights in our solar system are composed almost entirely of frozen water. Billions of ice particles, ranging in size from tiny dust grains to chunks as large as houses, orbit Saturn in perfect harmony. These ice particles are remarkably pure, reflecting sunlight with a brilliance that makes the rings appear almost luminous. The rings are incredibly thin compared to their width. If you could scale them down to the thickness of a piece of paper, they would stretch for several miles. Despite their solid appearance from a distance, the rings are mostly empty space, with ice particles following their own gentle orbits around the giant planet. Some scientists believe the rings might be relatively young in cosmic terms, perhaps formed when a comet or moon wandered too close to Saturn and was pulled apart by the planet's gravity, creating this spectacular display of cosmic debris transformed into beauty. Uranus rolls on its side like a cosmic bowling ball. While most planets spin like tops, rotating roughly upright as they orbit the Sun, Uranus does something wonderfully unusual. It tilts so far over that it essentially rolls along its orbital path, spinning on its side. This extreme tilt means that each pole of Uranus spends about 42 years in continuous sunlight, followed by 42 years of darkness. Imagine a world where summer and winter each last for decades, where one hemisphere basks in eternal daylight while the other experiences an endless polar night. This unusual orientation likely resulted from a collision with another large object billions of years ago, an ancient impact that knocked Uranus off its upright stance and set it rolling through space in its own unique way. Neptune's winds are the fastest in the solar system, yet they move with mysterious grace. On Neptune, the most distant major planet in our solar system, winds race across the deep blue atmosphere at speeds of up to 1,200 miles per hour. These are the fastest sustained winds found anywhere in the solar system, moving with such incredible velocity that they could circle Earth in just a few hours. What makes this even more remarkable is that Neptune receives only 1/10,000th of the sunlight that Earth does, yet somehow it generates these powerful atmospheric currents. The planet radiates more heat than it receives from the distant Sun, suggesting an internal energy source that drives these magnificent wind patterns. Despite their incredible speed, these winds create beautiful, flowing clouds, deformations that drift across Neptune's azure surface like brushstrokes on a cosmic canvas. the asteroid belt contains less mass than our moon. Between Mars and Jupiter lies a region filled with countless rocky objects called the asteroid belt, and despite what science fiction might suggest, it's mostly empty space. All the asteroids in the belt combined would have less mass than Earth's moon. If you were traveling through the asteroid belt, you would likely see nothing but empty space in every direction, with the occasional distant glint of sunlight reflecting off a tumbling rock. The largest object in the asteroid belt is Ceres, now classified as a dwarf planet, which contains about 1/3 of the belt's total mass. These ancient fragments are remnants from the solar system's formation, pieces that never quite came together to form a planet. Instead, maintaining their quiet orbit between the inner and outer planets like cosmic museum pieces, preserving the memory of our system's birth. Io, Jupiter's moon, has active volcanoes that paint its surface in brilliant colors. Among Jupiter's many moons, Io stands out as one of the most volcanically active bodies in the solar system. Its surface is constantly being reshaped by eruptions that spew sulfur compounds high into space, creating a landscape painted in vivid yellows, oranges, and reds. Unlike volcanic activity on Earth, which is driven by our planet's internal heat, Io's volcanoes are powered by the constant gravitational squeeze it experiences from Jupiter, and tidal heating keeps its neighboring moons. This Io's interior molten and active, creating fountains of lava that can shoot hundreds of miles into space before gently falling back to the surface. The moon has no impact craters because its surface is so young, constantly renewed by this ongoing volcanic activity that acts like a cosmic artist continuously repainting the canvas. Europa may harbor more water than all of Earth's oceans combined. Beneath Europa's smooth, icy surface lies one of the most intriguing secrets in our solar system. This moon of Jupiter is covered by a frozen shell of water ice, but underneath that protective layer, scientists believe there exists a vast liquid ocean. This hidden sea may contain twice as much water as all of Earth's oceans combined, kept liquid by the same tidal heating that affects Io. The surface of Europa is remarkably smooth and young, crisscrossed by long lines and cracks that suggest the ice shell moves and shifts over the liquid beneath. In some places, the ice may be only a few miles thick, and there's evidence that water occasionally erupts through cracks to the surface, creating geysers that spray into space before freezing and falling back down like snow. Titan has lakes and rivers, but they're filled with liquid methane. Saturn's largest moon, Titan, is the only other body in our solar system known to have stable liquid on its surface. But instead of water, Titan's lakes and rivers flow with liquid methane and ethane. The moon has a thick atmosphere and a weather cycle remarkably similar to Earth's, complete with clouds, rain, and seasonal evaporates from the lake's changes. Methane forms clouds in the orange sky, and then falls as rain that carves river channels and fills lake beds. The largest of these methane seas, Kraken Mare, is larger than the Caspian Sea on Earth. Titan's landscape includes mountains, valleys, and shorelines that would look familiar to us, even though they're carved from water ice as hard as rock and filled with hydrocarbons instead of water. Pluto has a heart-shaped feature that captured our imagination. When the New Horizons spacecraft flew by Pluto in 2015, It revealed a world far more complex and beautiful than anyone had imagined. The most striking feature is a large, bright, heart-shaped plane called Tombaugh Regio, named after Pluto's discoverer. This heart is actually a vast plain of nitrogen ice, smooth and bright, that reflects sunlight like a cosmic valentine. The heart shape appears to be maintained by the slow circulation of nitrogen ice, which sublimates into gas on one side and condenses back to ice on the other side, creating a gentle, eternal cycle. Pluto's surface also features towering mountains made of water ice, vast plains, and possible cryovolcanoes that may erupt not lava, but liquid water and organic compounds. Comets are ancient time capsules from the birth of the solar system. These wandering ice balls spend most of their time in the cold, dark outer reaches of the solar system, preserved in a deep freeze that keeps them virtually unchanged since the solar system formed over 4 billion years ago. When a comet's elongated orbit brings it close to the Sun, the ice begins to sublime, turning directly from solid to gas and creating the beautiful glowing coma and tail that we sometimes see from Earth. The tail always points away from the Sun, pushed by solar wind and radiation pressure, creating a cosmic streamer that can stretch for millions of miles. Each comet is unique, carrying its own mixture of water ice, frozen gases, and dust that tells a story about the conditions present when our solar system was young. The Sun contains more than 99% of all the mass in our solar system. Our Sun is so massive that it contains more matter than all the planets, moons, asteroids, and comets combined. This incredible gravitational dominance is what keeps our entire solar system in its gentle, predictable dance. The Sun's immense gravity reaches out across billions of miles, holding distant Pluto in its orbit and maintaining the delicate balance that allows planets to follow their paths around it year after year. Despite its overwhelming mass, the Sun is primarily made of the two lightest elements in the universe, hydrogen and helium, which fuse together in its core to create the light and heat that warm our world and make life possible. Each planet rotates at its own unique pace, like cosmic dancers keeping different rhythms. While Earth completes one rotation every 24 hours, creating our familiar cycle of day and night, each world in our solar system moves to its own tempo. Mercury spins slowly, taking 59 Earth days to turn once on its axis, while Jupiter, despite its enormous size, completes a rotation in less than 10 hours, making its days shorter than ours. This variety in rotation speeds means that time itself feels different on each world. A day on Venus lasts longer than a Venusian year, while a day on Jupiter passes by in the blink of an eye compared to our earthly experience. The solar system is mostly empty space, creating a sense of vast, peaceful solitude. If you could shrink the solar system down to the size of a football field, the Sun would be smaller than a marble at the center, and Earth would be a grain of sand about 25 yards away. The nearest star beyond our Sun would be located roughly 4,000 miles from that football field. This immense scale means that the solar system is primarily a quiet void, with tiny worlds separated by enormous distances, each following its solitary path through space. Even within the asteroid belt, you would need to travel thousands of miles to encounter the next object, creating a sense of profound cosmic solitude that is both humbling and peaceful. And now, As these gentle facts about our solar system settle into your thoughts like stardust on a calm night, let yourself drift deeper into rest. We've journeyed from the backward spinning of Venus to the heart-shaped plains of Pluto, from the hidden oceans of Europa to the methane lakes of Titan. Each world in our cosmic neighborhood has its own quiet story, its own rhythm, its own way of dancing through the darkness. You are part of this solar system, riding on Earth as it glides through space, breathing air that has been stirred by solar winds, warmed by light that began its journey in the nuclear heart of our sun. In this moment, as you rest, the planets continue their ancient orbits. Moons rise and set on distant worlds, and comets trace their long, slow paths through the outer darkness. Let these peaceful worlds carry your dreams tonight, and know that tomorrow they will still be there, quietly spinning through space, waiting to inspire wonder in anyone who looks up at the sky. The moons of our solar system number in the hundreds, each a world unto itself. Beyond the few famous names we know, there are countless smaller satellites drifting quietly around their parent planets. Jupiter alone has at least 95 known moons, from massive Ganymede, larger than Mercury, to tiny irregular chunks of rock captured long ago by the giant planet's gravity. Saturn hosts 146 confirmed moons, each following its own orbital path like notes in a cosmic symphony. Some of these moons are spherical and smooth, shaped by their own gravity into perfect worlds. Others are lumpy, potato-shaped fragments that tumble end over end as they orbit. Many were likely asteroids or comets that wandered too close to a planet and were gently captured, becoming permanent companions in an endless dance around their new home. The Great Red Spot on Jupiter has been raging for centuries, a storm larger than Earth itself. This massive anticyclonic storm has been observed for over 400 years, making it one of the longest-lived weather systems known to science. The Great Red Spot is so large that 2 or 3 Earths could fit comfortably inside its swirling boundaries. What makes this storm even more remarkable is its stability. While hurricanes on Earth last for days or weeks at most, Jupiter's Great Red Spot has maintained its distinctive oval shape and rusty red color for centuries. The storm rotates counterclockwise, completing one full rotation every 6 Earth days. Its distinctive color likely comes from complex organic compounds created by the interaction of Jupiter's atmospheric chemistry with sunlight and cosmic radiation. Recently, astronomers have noticed that the Great Red Spot appears to be slowly shrinking, though it remains a dominant feature of Jupiter's turbulent atmosphere. Solar wind creates invisible rivers flowing throughout our solar system. The sun doesn't just emit light and heat. It also sends out a constant stream of charged particles called the solar wind, which flows outward from the sun's corona at speeds of hundreds of miles per second. This invisible wind fills the entire solar system, creating what scientists call the heliosphere, a vast bubble of solar influence that extends far beyond the orbit of Pluto. The solar wind interacts with planetary magnetic fields and atmospheres in beautiful ways. On Earth, it creates the auroras that dance across polar skies when solar particles are channeled by our magnetic field toward the poles. Other planets experience their own versions of these light displays. The solar wind also pushes against comet tails, always directing them away from the sun regardless of the comet's direction of travel through space. Each planet has its own unique collection of chemical elements and compounds. While all the planets formed from the same original disk of material around the young sun, their different distances from our star and varying sizes led to remarkably diverse compositions. The inner rocky planets are rich in silicates, metals, and other materials that could remain solid close to the sun's heat. Venus has an atmosphere of carbon dioxide so dense it creates a runaway greenhouse effect, while Mars has a thin atmosphere that allows temperatures to swing dramatically. The outer gas giants captured vast amounts of hydrogen and helium, the most abundant elements in the universe, along with water, methane, and ammonia ices. These differences mean that each world has its own chemical fingerprint, its own unique blend of elements that tells the story of how and where it formed. Ganymede, Jupiter's largest moon, generates its own magnetic field. Among all the moons in our solar system, Ganymede holds a special distinction. It's the only moon known to generate its own magnetic field, likely produced by a partially molten iron core deep within its interior. This magnetic field creates a protective bubble around Ganymede, shielding parts of its surface from Jupiter's intense radiation. The moon is also remarkable for its size, being larger than Mercury and containing more water than all of Earth's oceans. Ganymede's surface tells a story of geological activity, with darker, heavily cratered regions representing ancient terrain, and brighter areas showing evidence of more recent geological processes. The Hubble Space Telescope has even detected evidence of a thin oxygen atmosphere around Ganymede, created when radiation splits water molecules on the moon's icy surface. Enceladus sprays fountains of water into space from its south pole. Saturn's small moon. Enceladus appeared unremarkable until the Cassini spacecraft revealed one of the most spectacular discoveries in our solar system. From long cracks near its south pole called tiger stripes, Enceladus shoots enormous geysers of water vapor and ice particles hundreds of miles into space. These fountains contain salt and organic compounds, suggesting they originate from a subsurface ocean beneath the moon's icy crust. The geysers are so powerful that some of the ejected material escapes Enceladus entirely and becomes part of Saturn's E-ring. The discovery of these water plumes, combined with evidence of hydrothermal activity on the ocean floor, makes Enceladus one of the most promising places in our solar system to search for conditions that might support life. The Kuiper Belt extends our solar system far beyond Neptune's orbit. In the cold, dark reaches beyond Neptune lies a vast region filled with icy bodies left over from the solar system's formation. The Kuiper Belt stretches from about Neptune's distance to roughly twice that far from the Sun, containing thousands of objects made primarily of frozen water, methane, and ammonia. Pluto is the most famous resident of this region, but it's joined by many other dwarf planets and countless smaller bodies. These objects represent some of the most pristine materials from the early solar system, preserved in the deep freeze of the outer reaches. Many comets that visit the inner solar system originate from the Kuiper Belt, beginning epic journeys that can take thousands of years to complete. Ceres, the largest object in the asteroid belt, has mysterious bright spots that reflect sunlight. When the Dawn spacecraft arrived at Ceres in 2015, it revealed a world far more complex than expected. The dwarf planet is covered with dark, carbon-rich material, but scattered across its surface are dozens of brilliant white spots that shine like beacons against the darker terrain. The most prominent of these bright features are located in Akator crater, where highly reflective sodium carbonate deposits create an almost mirror-like surface. These deposits likely formed when briny water from Ceres's interior was brought to the surface through impacts or cryovolcanic activity. The presence of these salts and evidence of past water activity suggests that Ceres may have had, or still has, a subsurface ocean, making this asteroid belt dwarf planet another potentially interesting world for understanding the conditions necessary for life. The solar system's planets can be divided into two distinct families with very different characteristics. The four inner planets, Mercury, Venus, Earth, and Mars, are small, rocky worlds with solid surfaces you could theoretically walk on. They're sometimes called terrestrial planets because they're similar in structure to Earth. These worlds formed close to the Sun, where temperatures were high enough that only rocky materials and metals could condense from the solar nebula. The four outer planets, Jupiter, Saturn, Uranus, and Neptune, are gas and ice giants with no solid surfaces, at least not that we could reach. They formed in the cooler outer regions of the solar system, where water and other compounds could freeze, allowing them to grow large enough to capture vast atmospheres of hydrogen and helium. This division creates two very different neighborhoods in our solar system, each with its own character and family of worlds. Phobos, Mars's largest moon, is slowly spiraling inward toward the planet. Mars has two small moons, Phobos and Deimos, both probably captured asteroids that were pulled in by the red planet's gravity long ago. Phobos, the larger and closer of the two, follows such a tight orbit around Mars that it completes 3 full orbits every Martian day. But this rapid orbital dance comes with a cost. Tidal forces are gradually slowing Phobos down, causing it to spiral inward toward Mars at a rate of about 6 feet per century. In approximately 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces to form a ring system around the planet. The Moon is already showing signs of stress, with long grooves across its surface that may be early fractures caused by Mars's gravitational pull. The Sun's surface has a lower temperature than its corona, creating one of astronomy's greatest mysteries. While the Sun's visible surface, called the photosphere, has a temperature of about 10,000 degrees Fahrenheit, the corona, the Sun's outer atmosphere visible during solar eclipses, reaches temperatures exceeding 2 million degrees Fahrenheit. This seems to violate our everyday experience that things should get cooler as you move away from a heat source. Scientists are still working to fully understand this coronal heating problem, though they believe it involves complex interactions between the Sun's magnetic field and the charged particles in its atmosphere. The corona's extreme heat drives the solar wind that flows throughout our solar system, making this temperature mystery one that affects the entire solar system's environment. Each planet experiences seasons differently based on its axial tilt and orbital characteristics. Earth's seasons are caused by our planet's 23-degree tilt relative to its orbital plane, creating the familiar cycle of spring, summer, fall, and winter as different hemispheres receive the year. Mars, varying amounts of sunlight throughout, has a similar tilt to Earth and experiences recognizable seasons, though they last about twice as long due to Mars's longer orbital period. Jupiter and Venus have almost no tilt, so they experience virtually no seasonal changes. Uranus, with its extreme 98-degree tilt, has the most unusual seasons in the solar system, with each pole experiencing 42 years of continuous daylight, followed by 42 years of darkness. Saturn's seasons last about 7 Earth years each, and we've been able to observe dramatic changes in its atmosphere and ring system as the planet progresses through its long seasonal cycle. The space between planets is filled with a tenuous medium of gas and dust. Interplanetary space isn't completely empty, but contains a thin distribution of particles from various sources. The solar wind contributes charged particles, while dust grains come from comet tails, asteroid collisions, and even interstellar space. This interplanetary medium is incredibly sparse compared to any vacuum we can create on Earth, but it's still measurable and plays important roles in solar system dynamics. Spacecraft traveling between planets must account for this medium, which can slowly erode surfaces and affect sensitive instruments over long journeys. The density of this material varies throughout the solar system, being denser closer to the Sun and in the plane where most planets orbit. Miranda, one of Uranus's moons, has the most dramatic and chaotic terrain in the solar system. This small moon appears to have been completely torn apart and reassembled at least once in its history, creating a surface that looks like a cosmic patchwork quilt. Miranda displays an incredible variety of geological features crammed into a tiny world only 300 miles across. There are regions of ancient, heavily cratered terrain alongside areas of dramatic cliffs, deep canyons, and strange, angular formations unlike anything seen elsewhere. One cliff on Miranda, called Verona Rupes, is over 12 miles high, making it one of the tallest known cliffs in the solar system. If you could somehow fall from the top of this cliff in Miranda's weak gravity, it would take about 12 minutes to reach the bottom. And now, as we drift further into the quiet depths of our solar system tour, let these gentle worlds continue to carry your thoughts toward rest. Each moon and planet we've visited has its own story written in ice and rock, in swirling atmospheres and ancient craters. From the geysers of Enceladus to the chaotic terrain of Miranda, from the great red spot's centuries-long storm to the bright spots of Ceres, our solar system reveals itself as a place of endless, gentle wonders. You are traveling through space right now, riding Earth as it glides along its orbital path at 67,000 miles per hour, yet feeling only the peaceful stillness of a quiet night. The moon above you is slowly moving away, growing more distant by the width of a fingernail each year. Jupiter's moons are dancing their gravitational ballet, while Saturn's rings catch starlight in their icy embrace. The solar system formed from a slowly spinning disk of dust and gas that collapsed over millions of years. About 4.5 billion years ago, our corner of the galaxy was filled with a vast nebula, a gentle cloud of hydrogen, helium, and heavier elements forged in the hearts of ancient stars. This nebula began to collapse under its own gravity, perhaps triggered by the shock wave from a nearby supernova or simply by the natural density fluctuations within the cloud. As it contracted, it began to spin faster, flattening into a disk with the proto-sun forming at its dense center. The temperature and pressure conditions at different distances from the forming sun determined what materials could condense and form solid particles. Close to the sun, only metals and rocky materials could survive the heat, while farther out, water and other volatiles could freeze into ice. This process of gradual accretion, where tiny particles stuck together to form larger and larger objects, eventually gave birth to the planets, moons, and smaller bodies we see today. The Oort cloud surrounds our entire solar system in a vast, spherical shell of icy objects. Far beyond the Kuiper belt, at distances so great that the sun appears as just another star, lies a theoretical region called the Oort cloud. This spherical shell of perhaps trillions of icy objects extends from about 2,000 times Earth's distance from the sun to nearly halfway to the nearest star. The objects in the Oort cloud are thought to be pristine remnants from the solar system's formation, ejected to these distant orbits by gravitational interactions with the giant planets during the early, chaotic period of solar system evolution. Most long-period comets, those that take hundreds or thousands of years to complete their orbits, are believed to originate from this distant reservoir. When passing stars or galactic tides occasionally disturb these icy bodies, some begin the long journey inward toward the sun, eventually becoming the spectacular comet we sometimes observe from Earth. Triton, Neptune's largest moon, orbits backward and may be a captured Kuiper belt object. Among all the large moons in our solar system, Triton is unique in that it follows a retrograde orbit, moving in the opposite direction to Neptune's rotation. This unusual orbital characteristic, combined with Triton's composition and size, suggests that it wasn't formed alongside Neptune, but was instead a large Kuiper belt object that wandered too close and was captured by the ice giant's gravity. Triton is one of the most fascinating worlds in the outer solar system, with active geysers that shoot dark particles up to 5 miles high into its thin atmosphere. The moon's surface is young and complex, showing evidence of geological activity that has erased most impact craters. Its retrograde orbit means that tidal forces are gradually slowing Triton down, and in the far future, it will either crash into Neptune or be torn apart to form a spectacular ring system. The sun loses about 4 million tons of mass every second through nuclear fusion. Deep within the sun's core, hydrogen nuclei are being fused into helium at temperatures exceeding 27 million degrees Fahrenheit. This process converts a tiny amount of matter directly into energy, following Einstein's famous equation E equals mc squared. Every second, about 600 million tons of hydrogen are converted into 596 million tons of helium, with the missing 4 million tons transformed into the energy that lights and warms our solar system. This might sound like a lot, but the sun is so massive that it can continue this process for another 5 billion years before running out of hydrogen fuel in its core. The energy produced in the core takes thousands of years to work its way to the surface, meaning the sunlight we see today actually began its journey during the last ice age. Icephatus, one of Saturn's moons, has a mysterious ridge that runs around its entire equator. This small, icy moon displays one of the most puzzling features in the solar system. a massive mountain ridge that extends nearly 800 miles along its equator, reaching heights of up to 12 miles. The ridge gives Iapetus a distinctive walnut-like appearance and remains one of the great mysteries of planetary science. No other moon in the solar system has anything resembling this feature. Some theories suggest it formed when Iapetus was spinning much faster in its youth, while others propose it might be the remnant of a collapsed ring system. Adding to Iapetus's mysterious nature is its dramatic color contrast, with one hemisphere being much darker than the other, as if the moon were painted half black and half white. The solar system travels through the galaxy at 515,000 miles per hour. Our entire solar system, including the Sun and all its orbiting bodies, is moving through the Milky Way galaxy at tremendous speed. We're currently located in one of the galaxy's spiral arms, about 26,000 light-years from the galactic center, following an orbit that takes approximately 225 to 250 million years to complete. During Earth's long history, our solar system has completed only about 20 of these galactic orbits. The last time we were in our current position in the galaxy, the supercontinent Pangaea was just beginning to break apart, and the age of dinosaurs had not yet begun. This motion through the galaxy also means we're constantly encountering different regions of interstellar space with varying densities of gas, dust, and cosmic radiation. Callisto, another of Jupiter's large moons, has the most heavily cratered surface in the solar system. This ancient world bears the scars of 4 billion years of impacts, creating a surface so densely packed with craters that new impacts simply erase older ones. Unlike the other large moons of Jupiter, Callisto shows no evidence of geological activity that might have erased or modified its ancient surface. The moon's dark, icy surface reflects only about 20% of the sunlight that hits it, giving it a somber, timeless appearance. Despite its battered exterior, Callisto may harbor a subsurface ocean beneath its icy crust, kept liquid by the decay of radioactive elements within the moon's rocky core. This makes Callisto another potential harbor for life in the outer solar system, hidden beneath a surface that tells the violent story of the solar system's early bombardment period. The heliopause marks the boundary where the solar wind meets interstellar space. Far beyond the orbit of Pluto, at a distance roughly 4 times greater than Neptune's orbit, lies the heliopause, the boundary where our sun's influence gives way to the interstellar medium. Here, the solar wind, which has been flowing outward from the sun at hundreds of miles per second, finally meets the pressure of interstellar gas and can travel no further. This creates a kind of cosmic shoreline, the edge of our solar system's bubble of influence within the galaxy. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. The heliopause is not a fixed boundary, but fluctuates like a breathing membrane as the solar wind's strength varies and as our solar system moves through regions of the galaxy with different densities of interstellar material. Venus has surface pressure 90 times greater than Earth's, equivalent to being half a mile underwater. The dense carbon dioxide atmosphere of Venus creates a surface pressure so intense that it would instantly crush any spacecraft not specifically designed to withstand it. This crushing atmosphere is also responsible for Venus's extreme greenhouse effect, trapping heat so efficiently that surface temperatures reach 900 degrees Fahrenheit, hot enough to melt lead. The atmosphere is so thick that it would feel more like moving through liquid than gas. Russian spacecraft that have landed on Venus's surface have survived only minutes to hours before being destroyed by the combination of crushing pressure, corrosive atmosphere, and extreme heat. Despite these hostile conditions, the upper atmosphere of Venus is much more hospitable, with temperatures and pressures similar to Earth's surface, leading some scientists to propose floating research stations that could study this mysterious world from above. The solar system contains several dwarf planets, each with its own unique characteristics. Beyond the 8 major planets lies a diverse collection of smaller worlds that don't quite qualify as full planets, but are too large and complex to be considered mere asteroids. Pluto, the most famous of these dwarf planets, has 5 known moons and a complex atmosphere that changes as it moves through its elliptical orbit. Eris, slightly smaller than Pluto but more massive, orbits so far from the Sun that it takes 557 Earth years to complete one orbit. Makemake, named after the creation deity of Easter Island's Rapa Nui people, has at least 1 moon and a surface covered in methane and ethane ices. Haumea is perhaps the strangest of all, shaped like an elongated football due to its rapid rotation, and accompanied by 2 small moons that may have formed when another object collided with Haumea billions of years ago. The moons of Mars are so small that their gravity is barely noticeable. Phobos and Deimos, the 2 tiny moons of Mars, are among the smallest moons in the solar system. Phobos, the larger of the 2, is only about 14 miles across at its widest point, while Deimos is even smaller at just 8 miles across. Their gravity is so weak that an astronaut on either moon could easily throw a baseball into orbit around the moon, or even escape its gravity entirely with a good strong throw. Both moons are irregularly shaped, looking more like captured asteroids than the spherical moons we're familiar with around Earth. They're both tidally locked to Mars, always showing the same face to the red planet, and they orbit so close that from Mars's surface, they would appear to move quickly across the sky, with Phobos rising in the west and setting in the east due to its rapid orbital motion. The largest canyon in the solar system stretches across Mars for over 2,500 miles. Valles Marineris is a vast system of canyons that dwarfs even the Grand Canyon, stretching roughly 1/5 of the way around Mars's equator. If this canyon system existed on Earth, it would span the entire width of the United States. The canyon reaches depths of up to 4 miles in some places and widths of up to 120 miles. Unlike the Grand Canyon, which was carved by flowing water over millions of years, Valles Marineris likely formed through tectonic processes as the planet's crust stretched and cracked during Mars's geological evolution. Some sections of the canyon may have been modified by ancient water flows, wind erosion, and landslides, creating a complex landscape that tells the story of Mars's geological history. Jupiter's moon Europa has a surface younger than the dinosaurs. Despite being billions of years old, Europa's icy surface shows very few impact craters, suggesting that it's geologically active and constantly renewing itself. Scientists estimate that the surface we see today is only about 40 to 90 million years old, making it younger than the time when dinosaurs roamed Earth. This youthful appearance is likely due to the constant flexing and cracking of Europa's ice shell as it orbits Jupiter. The gravitational tidal forces from Jupiter and Europa's neighboring moons keep the ice in constant motion, creating new surface features and erasing old ones. Long linear cracks called lineae crisscross the surface, and some regions show evidence of chaos terrain where the ice shell appears to have been broken up and refrozen in jumbled patterns. The solar wind creates a constantly changing bubble around our solar system. The heliosphere, the region of space dominated by the solar wind, is not static, but expands and contracts like a breathing organism based on the sun's activity levels. During periods of high solar activity, when the sun produces more energetic particles and stronger magnetic fields, the heliosphere expands outward. During quieter periods, it contracts. This breathing motion affects the entire solar system, influencing the radiation environment around planets and the paths that cosmic rays take as they try to enter our solar system from interstellar space. The shape of the heliosphere is also influenced by our solar system's motion through the galaxy and the magnetic field and density of the interstellar medium we're currently passing through. Hyperion, one of Saturn's moons, tumbles chaotically rather than rotating in a regular pattern. Most moons and planets have predictable rotational periods, spinning on their axes in regular cycles. Hyperion, however, follows no such pattern. This irregularly shaped moon tumbles end over end in a chaotic rotation that makes it impossible to predict which face will be pointing towards Saturn at any given time. This chaotic rotation is caused by Hyperion's irregular shape and its resonant orbital relationship with Saturn's larger moon Titan. The gravitational tugs from Saturn and Titan, combined with Hyperion's asymmetric mass distribution, create a complex, dynamical situation that results in this unpredictable tumbling motion. Hyperion's surface is also unusual, covered in a strange, sponge-like terrain of deep craters and ridges that give it an appearance unlike any other moon in the solar system. The temperature difference between day and night on Mercury is greater than on any other planet. Mercury's lack of atmosphere means there's nothing to distribute heat around the planet or retain warmth during its long nights. On the day side, temperatures can reach 800 degrees Fahrenheit, while on the night side, they plummet to -300 degrees Fahrenheit. This creates a temperature swing of over 1,100 degrees, the largest in the solar system. Interestingly, Mercury's poles may contain water ice in permanently shadowed craters, even though the planet is the closest to the Sun. These polar regions never receive direct sunlight and remain cold enough for water ice to persist, creating some of the coldest places in the inner solar system on the same world that experiences some of the hottest temperatures. And now, as these quiet facts about our solar system continue to unfold like gentle waves, let your mind drift with them into deeper rest. We've traveled from the formation of worlds in ancient dust clouds to the chaotic tumbling of distant moons, from the crushing depths of Venus's atmosphere to the delicate ice geysers of distant satellites. Each world we've encountered carries its own rhythm, its own story written in stone and ice, in swirling gases and ancient impacts, Your journey through space continues even now as Earth carries you along its orbital path, while the moon pulls gently at the tides and the sun bathes our world in light that began its journey from the stellar core years before you were born. The planets maintain their stately dance. Moons rise and set on worlds you'll never visit, and in the cold outer reaches, ancient comets begin their slow journeys toward the inner solar system. Let these cosmic rhythms carry your dreams tonight. These gentle worlds that spin and orbit in the vast quietude of space. Tomorrow, they will still be there, following their eternal paths, waiting to inspire wonder in anyone who pauses to consider the magnificent, peaceful complexity of our solar system home. Meteors burn up in our atmosphere every day, creating tiny shooting stars most of us never see. While we often think of meteor showers as rare celestial events, Earth is actually bombarded with space debris constantly. Every day, our planet encounters roughly 100 tons of material from space, most of it no larger than grains of sand or pebbles. These tiny fragments, traveling at speeds of up to 45 miles per second, create brief streaks of light as they burn up in the upper atmosphere. Most are so faint they're invisible to the naked eye, but sensitive cameras and radar systems detect thousands of these micrometeors daily. The atmosphere acts as Earth's protective shield, vaporizing most of this cosmic dust before it can reach the surface. Occasionally, larger pieces survive the fiery journey and become meteorites, but the vast majority simply add their atoms to our planet's atmospheric inventory, having traveled millions or billions of miles through space, only to become part of the air we breathe. The great dark spot on Neptune comes and goes like a cosmic weather pattern. Unlike Jupiter's persistent Great Red Spot, Neptune's atmospheric features are more transient, appearing and disappearing over periods of years. When Voyager 2 flew by Neptune in 1989, it observed a massive dark oval storm about the size of Earth, dubbed the Great Dark Spot. This storm raged in the planet's southern hemisphere with winds exceeding 1,000 miles per hour. However, when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had vanished entirely, replaced by new storms in different locations. This dynamic behavior suggests that Neptune's atmosphere is more variable than Jupiter's, with storm systems forming, evolving, and dissipating on relatively short timescales. The planet's extreme distance from the Sun makes these powerful atmospheric dynamics even more mysterious, as there's very little solar energy available to drive such intense weather patterns. Vesta, the second largest asteroid, has a mountain taller than any peak on Earth. This massive asteroid, located in the asteroid belt between Mars and Jupiter, hosts a mountain near its south pole that rises about 13 miles above the surrounding terrain. This makes it nearly twice as tall as Mount Everest and comparable in height to Olympus Mons on Mars. The mountain likely formed during a massive impact that also created Vesta's distinctive south polar crater, one of the largest impact basins in the solar system relative to the size of the body it's on. The impact was so powerful that it blasted chunks of Vesta into space, some of which have fallen to Earth as meteorites, allowing scientists to study pieces of this distant world in laboratories. Vesta's surface shows evidence of complex geological processes, including ancient lava flows, making it more like a small planet than a typical asteroid. The solar system's largest moon has a stronger magnetic field than Mercury. Ganymede, Jupiter's massive satellite, not only holds the distinction of being larger than Mercury, but also possesses something that Mercury lacks: a strong, intrinsic magnetic field. While Mercury has only a weak magnetic field, Ganymede's is robust enough to create its own magnetosphere within Jupiter's much larger magnetic environment. This creates a complex, nested magnetic system where Ganymede's magnetic bubble sits within Jupiter's magnetic domain. The magnetic field likely originates from a liquid iron core within Ganymede, suggesting that this moon has remained geologically active despite its great age. This magnetic field helps protect parts of Ganymede's surface from Jupiter's intense radiation, creating relatively safe havens on a moon that would otherwise be bathed in lethal radiation. Saturn's hexagonal storm at its north pole is one of the most geometrically perfect features in nature. At Saturn's north pole sits one of the most unusual and visually striking atmospheric phenomena in the solar system: a nearly perfect hexagonal cloud pattern that has persisted for decades. Each side of this hexagon is approximately 9,000 miles long, making it wide enough for two Earths to fit inside. The hexagon rotates once every 10 hours and 39 minutes, matching Saturn's rotation period. At the center of this hexagonal structure lies a massive cyclonic storm with an eye wall similar to hurricanes on Earth. The precise geometric nature of this formation has puzzled scientists, though laboratory experiments have shown that rotating fluids can spontaneously form polygonal patterns under certain conditions. The hexagon appears to be a standing wave pattern in Saturn's atmosphere, a stable configuration that has maintained its shape through seasonal changes and varying illumination conditions. The dwarf planet Haumea spins so fast it has stretched itself into an oval shape. Located in the Kuiper belt beyond Neptune, Haumea completes one rotation in just under 4 hours, making it one of the fastest spinning large objects in the solar system. This rapid rotation has deformed the dwarf planet from a spherical shape into an elongated ellipsoid, roughly twice as long as it is wide. The centrifugal force from this spinning motion would actually fling material off Haumea's surface if it rotated just 20% faster. Haumea's surface appears to be covered in crystalline water ice, giving it a bright, reflective appearance. The dwarf planet has two small moons, Hi'iaka and Namaka, named after Hawaiian goddesses, which likely formed from material ejected during a massive collision that may also be responsible for Haumea's rapid rotation and unusual shape. Comets develop two distinct tails as they approach the Sun, each pointing in different directions. As a comet's orbit brings it closer to our star, solar radiation begins to vaporize the ice and dust on its surface, creating the characteristic glowing coma and tail. However, comets actually develop two separate tails with different compositions and behaviors. The dust tail is composed of heavier particles that are pushed away from the Sun by radiation pressure. But these particles follow the comet's orbital path, creating a curved tail that trails behind the comet. The gas or ion tail, made of electrically charged particles, is pushed directly away from the Sun by the solar wind, creating a straight tail that always points away from the Sun regardless of the comet's direction of travel. When Earth passes through the debris trail left by a comet's dust tail, We experience meteor showers as these particles burn up in our atmosphere. The asteroid belt contains a surprising amount of water, locked in clay minerals and hydrated rocks. While we often think of asteroids as dry, rocky bodies, many contain significant amounts of water bound up in their mineral structures. Spectroscopic observations have revealed that numerous asteroids in the belt between Mars and Jupiter show evidence of clay minerals and other hydrated compounds that formed in the presence of liquid water. Some asteroids may contain up to 20% water by mass, locked within their rocky matrices. This discovery has important implications for understanding the early solar system and the distribution of water throughout our cosmic neighborhood. Some scientists propose that asteroids like these may have delivered much of Earth's water through impacts during the planet's early history, making these ancient rocks potential sources of the oceans we depend on today. Jupiter acts as a cosmic vacuum cleaner, protecting the inner solar system from dangerous impacts. The giant planet's immense gravitational influence serves as both a shield and a trap for potentially hazardous objects. Comets and asteroids that venture into the outer solar system often find their paths altered by Jupiter's gravity, either being flung out of the solar system entirely or captured into orbits around the giant planet. The Shoemaker-Levy 9 comet provided a dramatic demonstration of this protective role in 1994 when it broke apart and crashed into Jupiter in a series of spectacular impacts. Without Jupiter's gravitational influence, Earth would likely experience far more frequent and devastating impacts from space debris. However, Jupiter's role is complex, as it can also occasionally redirect objects toward the inner solar system, though the net effect appears to be protective for planets like Earth. The moons of Uranus are named after characters from Shakespeare and Alexander Pope, breaking the mythological naming tradition. While most planetary satellites bear names from Greek and Roman mythology, Uranus's 27 known moons draw their names from literary works. The largest moons, Titania, Oberon, Ariel, Umbriel, and Miranda, are named after characters from Shakespeare's plays, while smaller moons bear names from Pope's The Rape of the Lock. This unique naming convention reflects the distinctive character of the Uranian system, which orbits on its side and possesses its own peculiar dynamics. Many of these moons show evidence of past geological activity, with complex surface features that tell stories of ancient impacts, tectonic processes, and possibly cryovolcanic activity. The naming choice gives the Uranian system a poetic quality that seems fitting for these distant, mysterious worlds orbiting the tilted ice giant. Pluto's orbit is so elliptical that it sometimes comes closer to the Sun than Neptune. During its 248-year journey around the Sun, Pluto follows such an elongated path that for about 20 years of each orbit, it actually travels closer to the Sun than Neptune. The most recent time this occurred was from 1979 to 1999, when Pluto held the distinction of being the 8th planet from the Sun rather than the 9th. This unusual orbital characteristic is due to Pluto's high orbital eccentricity and inclination, which causes its path to be tilted relative to the plane where most other planets orbit. Despite this orbital crossing, Pluto and Neptune will never collide because they are locked in a gravitational resonance. with Pluto completing exactly 2 orbits for every 3 of Neptune's. This stable relationship has persisted for millions of years and will continue far into the future. The solar system contains vast amounts of organic compounds, the building blocks of life. Throughout our cosmic neighborhood, from the atmospheres of gas giants to the surfaces of distant moons and the nuclei of comets, scientists have detected complex organic molecules. Titan's thick atmosphere contains methane, ethane, and more complex hydrocarbons, while its surface lakes hold liquid versions of these compounds. Comets carry a rich inventory of organic materials that were preserved in the deep freeze of the outer solar system since the time of formation. Even some asteroids and meteorites contain amino acids and other organic compounds that could serve as precursors to biological molecules. This widespread distribution of organic chemistry suggests that the raw materials for life are common throughout the solar system. Though the step from chemistry to biology remains one of the greatest mysteries in science, the Sun's magnetic field reverses completely every 11 years in a process that affects the entire solar system. Our star's magnetic field is not constant, but follows a complex cycle that sees the north and south magnetic poles switch places roughly every 11 years. This solar magnetic cycle drives the sunspot cycle and influences solar activity throughout the system. During periods of high magnetic activity, the Sun produces more solar flares, coronal mass ejections, and intense solar wind, all of which can affect planetary atmospheres, satellite operations, and even terrestrial weather patterns. The Sun's magnetic field lines extend throughout the solar system via the solar wind, creating a complex, ever-changing magnetic environment that influences how cosmic rays penetrate our local space neighborhood and affects the aurora displays on planets with magnetic fields. Some of Saturn's moons share orbits, following each other like celestial dance partners. Among Saturn's numerous satellites are several pairs of small moons that share nearly identical orbital paths around the planet. Janus and Epimetheus are perhaps the most famous of these co-orbital moons, following orbits that are only about 30 miles apart. Every 4 years, these moons approach each other, and their mutual gravitational attraction causes them to swap orbits in an elegant celestial dance. The inner moon moves to the outer orbit, while the outer moon drops to the inner orbit, and they then spend the next 4 years moving apart until they meet again on the opposite side of Saturn. Other moon pairs, like Telesto and Calypso with Tethys, occupy special gravitational points called Lagrange points, where they remain in stable positions relative to their larger companion. The solar system is still evolving and changing, even after 4.5 billion years. While we often think of planetary orbits as fixed and eternal, the solar system remains a dynamic environment where subtle changes accumulate over cosmic time. The moon continues to recede from Earth, gradually slowing our planet's rotation and lengthening our days. Mars may eventually capture one of the passing asteroids as a third moon. The orbits of the planets themselves shift slightly due to gravitational interactions, and computer simulations suggest that the inner solar system's orbital configuration may become unstable in the far future. Some of the smaller moons around the gas giants will eventually spiral into their parent planets or be ejected entirely. Even the Sun's increasing luminosity will gradually alter conditions throughout the system. These changes occur so slowly that they're imperceptible on human timescales. But they remind us that even the most stable-seeming celestial arrangements are temporary when viewed across deep time. Every planet in our solar system could fit in the space between Earth and the Moon with room to spare. The average distance between Earth and its satellite is about 238,855 miles, which seems like an enormous gap. However, if you were to line up all the planets in our solar system side by side, including Jupiter with its massive 88,000-mile diameter, the total would span approximately 235,000 miles, leaving about 4,000 miles of extra space. This surprising fact illustrates just how much empty space exists in our cosmic neighborhood and helps put the vast scales of the solar system into perspective. The calculation becomes even more remarkable when you consider that Jupiter alone accounts for more than a third of this combined diameter, emphasizing the giant planet's dominance in our solar system's family of worlds. The great red spot on Jupiter is shrinking, and scientists aren't sure why. Historical observations show that Jupiter's famous storm has been gradually decreasing in size for over a century. When first observed in the 1800s, the Great Red Spot was large enough to fit 3 Earths inside it. Today, it's only about 1.5 Earth diameters across, and the rate of shrinkage appears to be accelerating. Recent observations suggest the storm is also changing shape, becoming more circular rather than oval, and its color has varied from deep red to pale orange over the decades. The mechanisms driving these changes remain mysterious, though they may be related to interactions with other atmospheric features, changes in Jupiter's internal heat flow, or shifts in the planet's atmospheric chemistry. Some scientists speculate that the Great Red Spot might eventually disappear entirely, bringing an end to one of the solar system's most iconic features. And now, as these gentle revelations about our solar system continue to wash over you like a calm tide, let your thoughts drift even deeper into the peaceful embrace of sleep. We've journeyed from the geometric perfection of Saturn's hexagonal storm to the literary names of Uranus's moons, from the protective influence of Jupiter to the shrinking majesty of its great red spot. Each world we've encountered spins quietly through space, following laws of physics that create beauty, mystery, and endless variation in the cosmic dance. The solar system breathes around you as you rest, planets wheeling through their orbits, moons waxing and waning in alien skies, and ancient comets beginning their slow pilgrimages toward the sun. Meteors streak silently through the vacuum of space, while magnetic fields shift and flow like invisible rivers throughout our stellar neighborhood. In the asteroid belt, chunks of rock tumble slowly end over end, and in the Kuiper belt beyond, icy worlds drift in the eternal twilight of the outer system. You are part of this magnificent clockwork, carried along on Earth's steady path through space, warmed by light that traveled 93 million miles to reach you, protected by a magnetic field that deflects the solar wind into beautiful aurora displays at the poles. The atoms in your body were forged in stellar cores and scattered through space by ancient supernovas, eventually finding their way into the disk of dust and gas that became our solar system, and finally into the world that cradles you now. Let these cosmic rhythms guide your dreams tonight. These ancient worlds that have been dancing through space since before life began on Earth. Tomorrow they will still be there, following their eternal choreography, waiting to inspire wonder in anyone who takes a moment to contemplate the serene complexity of our solar system home. The space between atoms in your body is proportionally as vast as the space between planets. If you could magnify an atom to the size of a football stadium, its nucleus would be smaller than a marble at the center, with electrons occupying spaces equivalent to the distant upper seats. This means that you, like everything else in the universe, are mostly empty space held together by invisible forces. The same fundamental architecture that governs the solar system, with its vast distances between worlds, exists within every cell of your body. Even in the most solid-seeming rock or the densest metal, atoms maintain these enormous gaps between their components. The forces that bind atomic particles together are similar in principle to the gravitational forces that keep planets in their orbits, creating patterns that repeat from the infinitesimally small to the cosmically large. The Voyager spacecraft are still sending signals back to Earth after decades in space. Launched in 1977, both Voyager 1 and Voyager 2 continue their journeys through the outer solar system and beyond, powered by the steady decay of plutonium in their radioisotope thermoelectric generators. These spacecraft have become humanity's most distant ambassadors, carrying golden records containing sounds and images from Earth as messages to any extraterrestrial life they might encounter. Voyager 1 crossed into interstellar space in 2012, becoming the first human-made object to leave the solar system's sphere of influence. Despite being billions of miles away, both spacecraft still communicate with Earth, though their signals take hours to reach us and arrive as whispers of radio waves that require enormous antennas to detect. Their instruments continue to make discoveries about the nature of interstellar space and the boundary between our solar system and the galaxy beyond. The atmospheric pressure on Mars is so low that liquid water immediately boils away. On the red planet's surface, the atmospheric pressure is less than 1% of Earth's, creating conditions similar to what you'd experience at an altitude of 100,000 feet above our world. This thin atmosphere means that liquid water cannot exist stably on Mars's surface under current conditions. Any water that emerges quickly boils and sublimes into vapor, regardless of temperature. However, this wasn't always the case. Ancient Mars had a thicker atmosphere and warm liquid water to floamer temperatures, allowing across its surface and carve the river valleys and lake beds we can still observe today. The planet's smaller size meant it couldn't hold on to its atmosphere as effectively as Earth, and over billions of years, much of it was stripped away by solar wind and escaped into space. Tidal forces from Earth are gradually slowing the moon's rotation, keeping the same face toward us always. This phenomenon, called tidal locking, means that the moon's rotational period matches its orbital period exactly, so we always see the same lunar hemisphere from Earth. The gravitational interaction between Earth and Moon creates bulges in both bodies, and the friction from these bulges acts as a brake on the Moon's rotation. Most large moons in the solar system are tidally locked to their parent planets, from Jupiter's Galilean satellites to many of Saturn's moons. This same tidal force that locked the moon's rotation is also gradually slowing Earth's rotation, making our days slightly longer over time. In the far future, Earth and Moon may become mutually tidally locked, with the same face of Earth always pointing toward the Moon, though this process would take billions of years to complete. The solar system's barycenter, the point around which all objects orbit, lies just outside the Sun's surface. While we often say that planets orbit the Sun, they actually orbit the center of mass of the entire solar system. For most of the solar system's history, this barycenter has been located within the Sun itself. But Jupiter's massive size and distance can pull it outside the Sun's surface. As the giant planets move through their orbits, the barycenter shifts position, sometimes lying within the Sun, and sometimes just beyond its edge. This subtle wobble in the Sun's motion can actually be detected by sensitive instruments and is one of the methods astronomers use to discover planets around other stars. When they observe a distant star wobbling slightly, it often indicates the presence of orbiting planets tugging on their star's position. Spacecraft experience different amounts of time depending on their speed and gravitational environment. Einstein's theories of relativity predict that time flows differently depending on motion and gravity, and these effects, though tiny, are measurable for spacecraft traveling through the solar system. GPS satellites, for example, must account for the fact that their clocks run slightly faster than Earth-based clocks due to the weaker gravitational field at their altitude and their orbital motion. For spacecraft traveling to the outer planets, these relativistic effects are small but real, causing their onboard clocks to gradually drift relative to Earth time. The effect becomes more pronounced near massive objects like the Sun or Jupiter, where stronger gravitational fields cause time to slow slightly. These subtle time dilations must be accounted for in precise navigation and communication with distant spacecraft. Some asteroids have their own tiny moons orbiting around them. As our understanding of the solar system has grown, we've discovered that many asteroids exist not as single objects, but as binary or even triple systems, with smaller rocks orbiting larger ones. These asteroid moons form through various processes, including impacts that chip off fragments or gravitational capture when two asteroids pass close together. The asteroid Ida was the first discovered to have a moon, a tiny satellite named Dactyl that orbits the larger rock every 20 hours. Some asteroids are actually contact binaries, two separate objects that have come together and stick to each other through their weak mutual gravity, creating peanut-shaped or dumbbell-shaped bodies. These complex gravitational relationships exist throughout the asteroid belt, creating miniature solar systems on scales measured in miles rather than millions of miles. The zodiacal light visible before dawn and after sunset comes from interplanetary dust. On clear, dark nights, you might notice a faint, triangular glow extending up from the horizon before sunrise or after sunset. This ethereal light, known as zodiacal light, is caused by sunlight scattering off countless tiny dust particles spread throughout the inner solar system. These particles come from comet tails, asteroid collisions, and debris left over from the solar system's formation. They form a disc-shaped cloud concentrated along the plane of planetary orbits, which is why the zodiacal light appears to follow the ecliptic across the sky. The dust particles are incredibly small, typically only micrometers across. But there are so many of them that they create a faint but detectable glow when illuminated by the sun. This interplanetary dust cloud extends throughout the solar system, gradually being replenished by ongoing cosmic processes. Mars has seasons similar to Earth's, but they last almost twice as long. The red planet's axial tilt is remark variations in temperature and weather similar to Earth's, creating seasonal patterns across its surface. However, Mars takes nearly 2 Earth years to complete one orbit around the Sun, so each Martian season lasts about 6 Earth months. Spring in Mars's northern hemisphere brings dust storms and the sublimation of carbon dioxide ice from the polar cap, while autumn sees the formation of new frost deposits as temperatures drop. The planet's elliptical orbit also affects its seasons, making southern hemisphere summers shorter but more intense than northern summers. During these southern summers, Mars is closest to the Sun, leading to more dramatic temperature swings and the potential for planet-wide dust storms that can last for months. The magnetic field lines of Jupiter create invisible highways for charged particles. Jupiter's powerful magnetic field, generated by electric currents in its metallic hydrogen core, creates a complex three-dimensional structure that extends millions of miles into space. Charged particles from the solar wind and from volcanic activity on Io follow these magnetic field lines like invisible railroad tracks, creating radiation belts that are far more intense than Earth's Van Allen belts. These trapped particles spiral along the magnetic field lines, bouncing back and forth between Jupiter's magnetic poles and creating a harsh radiation environment that can damage spacecraft electronics. The interaction between these particles and Jupiter's atmosphere creates aurora displays at both poles that are hundreds of times more energetic than Earth's northern and southern lights. Ceres shows evidence of recent geological activity despite being located in the asteroid belt. This dwarf planet, the largest object between Mars and Jupiter, has surprised scientists with signs of ongoing or recent cryovolcanic activity. Bright deposits of sodium carbonate salts in several craters suggest that briny water from Ceres's interior has reached the surface within the past few million years, a blink of an eye in geological terms. These deposits fade over time as they're exposed to space radiation, indicating that the processes creating them may still be active today. Ceres appears to have a differentiated interior with a rocky core and an icy mantle, possibly containing more fresh water than Earth. This makes the dwarf planet one of the most intriguing targets for understanding how water and potentially habitable conditions might exist throughout the solar system. The solar system passes through different regions of the galaxy, encountering varying cosmic environments. As our solar system orbits the center of the Milky Way, it moves through regions with different densities of interstellar gas, dust, and cosmic radiation. Currently, we're traveling through a relatively empty region called the local bubble, carved out by ancient supernova explosions that cleared away much of the surrounding material. This low-density environment allows the sun's solar wind to extend farther into space, creating a larger heliosphere than would exist in denser regions of the galaxy. In the past, Our solar system has moved through denser molecular clouds that may have compressed the heliosphere and exposed the planets to higher levels of cosmic radiation, potentially affecting atmospheric chemistry and climate patterns on Earth and other worlds. The retrograde rotation of Venus may have been caused by a massive impact early in solar system history. Computer simulations suggest that Venus originally rotated in the same direction as most other planets, but a collision with a large object, possibly as massive as a small planet, could have been powerful enough to reverse its spin entirely. This impact hypothesis could also explain why Venus has such a slow rotation rate and lacks a substantial magnetic field. The collision would have been catastrophic, potentially vaporizing much of Venus's early atmosphere and surface, which then recondensed over millions of years. Alternative theories propose that gravitational interactions with the Sun gradually slowed and eventually reversed Venus's rotation through tidal forces, though this process would require very specific conditions to work. Some of Jupiter's moons may have formed from the debris of earlier satellite systems. The complex gravitational environment around Jupiter has likely captured and destroyed multiple generations of moons throughout solar system history. The current system of large moons, the Galilean satellites, may have formed from a disk of debris left behind when earlier moon systems were disrupted by tidal forces or impacts. This process of satellite formation and destruction could explain some of the unusual characteristics of Jupiter's moon system, including the orbital resonances between Io, Europa, and Ganymede. Computer models suggest that massive planets like Jupiter may have gone through several cycles of moon formation, with each generation of satellites leaving traces that influenced the formation of the next. The day length on Earth has been gradually increasing throughout our planet's history. When Earth first formed, it rotated much faster than it does today, with days lasting only about 6 hours. The gravitational interaction with the Moon has been steadily slowing Earth's rotation through tidal friction, gradually lengthening our days. This process continues today, adding about 1.7 milliseconds to the length of a day every century. Ancient coral fossils show growth patterns that confirm shorter days in the distant past, with some 400-million-year-old specimens indicating days that were only about 22 hours long. The slowing rotation has also affected Earth's shape, as the planet has become slightly less flattened at the poles as its spin rate decreased. In the far future, if the Earth-Moon system remains stable, our planet's rotation will eventually slow to match the Moon's orbital period, creating days that last about 47 current days. The surface gravity on different worlds creates dramatically different experiences for any hypothetical visitors. On the Moon, with its gravity only 1/6 of Earth's, you could jump 6 times higher and objects would fall much more slowly. Mars, with 38% of Earth's gravity, would allow impressive leaps and make carrying heavy objects surprisingly easy. On Jupiter's cloud tops, however, the intense gravity would make every movement laborious, with your body weight increasing by 2.5 times. The extreme gravity differences also affect how atmospheres behave and how geological processes unfold on different worlds. Low gravity allows mountains to grow taller before they collapse under their own weight. while high gravity compresses atmospheres into denser layers and accelerates erosion processes. And now, as these quiet revelations about our solar system continue to unfold around you like a gentle embrace, let your consciousness drift even further into the peaceful depths of rest. We've explored the invisible architecture of atoms and the gradual slowing of planetary spins, the journeys of ancient spacecraft, and the complex gravitational dances that shape worlds across our cosmic neighborhood. Each fact we've shared carries within it the story of deep time, of forces acting across millions of years to create the serene complexity we observe today. The solar system continues its eternal motion around you as you sink deeper into sleep. Ancient impacts still echo in the backward spin of Venus, while tidal forces gradually reshape the orbits of moons and the rotation of planets. Dust particles from billion-year-old comets catch the morning sunlight, creating the zodiacal glow that has puzzled and enchanted observers for millennia. Magnetic field lines thread through space like invisible silk, guiding charged particles in their spiral dances around giant planets. Your atoms, forged in stellar cores and assembled through cosmic processes spanning eons, rest now in the temporary arrangement that is you, mostly empty space held together by forces that mirror the gravitational bonds keeping worlds in their orbits. The same fundamental patterns that govern the largest structures in the solar system also govern the smallest components of your being, creating a unity that connects you intimately with the cosmic dance unfolding in the darkness beyond Earth's atmosphere. Let these gentle cosmic rhythms carry you deeper into dreams, these patient worlds that have been spinning through space since before life began its long journey on Earth. The solar system breathes around you in cycles measured in years and centuries, in the slow drift of spacecraft through interstellar space and the gradual evolution of planetary systems. Tomorrow, when you wake, these worlds will still be there, following their ancient choreography, waiting to inspire wonder in anyone who pauses to contemplate the profound tranquility of our place in the cosmos. The rings of Saturn are constantly being renewed through a process of destruction and recreation. While these magnificent bands appear eternal and unchanging from our distant perspective, they exist in a state of dynamic equilibrium, with particles constantly colliding, breaking apart, and clumping together again. Shepherd moons orbit within and alongside the rings, their gravity sculpting sharp edges and creating gaps through gravitational resonances. Some ring particles are pulled into Saturn's atmosphere, where they vaporize and become part of the planet's upper atmospheric chemistry. New material is added when small moons are torn apart by tidal forces, or when meteoroid impacts blast fresh ice into space. This ongoing cycle of renewal means that the rings we see today may be quite different, errant from those that existed millions of years ago. Yet they maintain their overall structure through these gentle processes of cosmic recycling. The solar system contains several Trojan asteroids that share planetary orbits, following 60 degrees ahead or behind their host worlds. These gravitational hitchhikers occupy special points called Lagrange points, where the combined gravitational forces of the Sun and a planet create stable regions where smaller objects can remain for millions of years. Jupiter has the largest collection of Trojan asteroids, with over 9,000 discovered so far. divided into two groups named after heroes from opposite sides of the Trojan War. Mars, Neptune, and even Earth have their own smaller populations of these orbital companions. These ancient rocks provide glimpses into the early solar system's formation, preserved in their stable gravitational havens like cosmic time capsules that have avoided the collapse, issues and perturbations that have altered other small bodies throughout the system's history. The atmosphere of Jupiter contains water clouds that form at different altitudes, creating a complex, layered structure invisible from space. Beneath the familiar ammonia clouds that give Jupiter its banded appearance lie deeper layers where water vapor condenses into droplets and ice crystals. These water clouds exist at pressures and temperatures more similar to Earth's lower atmosphere, hidden beneath the colorful upper cloud decks we observe through telescopes. Lightning detected by spacecraft suggests vigorous convection within these water cloud layers, creating weather systems that dwarf any storm on Earth. The interaction between these different cloud layers, each composed of different chemical compounds, condensing at various temperatures and pressures, creates Jupiter's complex atmospheric dynamics and contributes to the beautiful patterns we see swirling across the giant planet's face. Solar eclipses occur throughout the solar system, not just on Earth, creating spectacular shadow displays on distant worlds. Any moon large enough to block its parent planet's view of the Sun can create an eclipse, and with over 200 moons in our solar system, these events happen frequently somewhere among the planets. Mars experiences eclipses when its small moons Phobos and Deimos pass in front of the Sun, though they appear more like dark spots crossing the solar disk rather than the total solar eclipses we know on Earth. Jupiter's large moons cast shadows on the planet's cloud tops, creating dark spots that can be observed racing across the giant planet's surface. These shadow events helped early astronomers calculate the speed of light by timing when Jupiter's moons appeared and disappeared as they moved behind the planet and through each other's shadows. The ice volcanoes on some moons erupt with water and organic compounds instead of molten rock. Cryovolcanism represents one of the most intriguing geological processes in the outer solar system, where liquid water, methane or ammonia takes the place of lava in creating volcanic activity. These eruptions are gentler than terrestrial volcanism, often appearing as geysers or fountains rather than explosive events. The heat driving these processes comes not from radioactive decay alone, but from tidal heating caused by gravitational interactions with massive parent planets. On worlds like Enceladus and Europa, these ice volcanoes may provide direct access to subsurface oceans, potentially bringing organic molecules and dissolved minerals from hidden seas to the surface, where they can be studied by passing spacecraft. The orbital resonances between moons create intricate gravitational music throughout the solar system. When moons orbit their parent planets at periods that form simple mathematical ratios, they lock into resonances that can persist for billions of years. Jupiter's moons, Io, Europa, and Ganymede, follow a precise 4:2:1 resonance, with Io completing 4 orbits for every 2 of Europa's and every 1 of Ganymede's. These resonances prevent the moons from crashing into each other and pump energy into their orbits, helping to maintain the tidal heating that keeps their interiors warm and potentially habitable. Similar resonant relationships exist throughout the solar system, from the rings of Saturn to the small moons of Uranus, creating a kind of celestial clockwork that demonstrates the elegant mathematical harmonies underlying planetary motion. The magnetotail of Jupiter stretches far beyond Saturn's orbit, creating one of the largest structures in the solar system. When the solar wind encounters Jupiter's powerful magnetic field, it compresses the field on the sun-facing side and stretches it into a long tail on the opposite side. This magnetotail extends for hundreds of millions of miles downstream from Jupiter, occasionally reaching past Saturn's orbit when solar wind conditions are just right. Within this enormous magnetic structure, charged particles are accelerated to high energies, and some are eventually ejected from the Jovian system entirely. The magnetotail creates a complex environment that affects not only Jupiter's moons, but potentially influences the magnetic environments of the outer planets when Jupiter's extended magnetic field sweeps past them during orbital alignments. Seasonal changes on Saturn create dramatic transformations in the planet's appearance and ring system. As Saturn follows its 29-year orbit around the Sun, the changing angle of sunlight illuminates different parts of the rings and reveals seasonal variations in the planet's atmosphere. During equinox, when the rings appear edge-on from Earth, they cast shadows on Saturn's atmosphere and become almost invisible, allowing astronomers to discover previously hidden moons and ring features. The changing seasons also affect the hexagonal storm at Saturn's North Pole, altering its color and intensity as different atmospheric layers receive varying amounts of solar heating. These long seasonal cycles mean that Saturn presents a constantly evolving appearance, with each observing season revealing new details about this magnificent world and its complex ring system. The escape velocity needed to leave different worlds varies dramatically, determining how easily atmospheres and over geological time. Earth's water can be retained. Escape velocity of 25,000 miles per hour requires significant energy for anything to break free of our planet's gravitational grip, helping us maintain our atmosphere and oceans over billions of years. Mars, with its lower gravity, has an escape velocity of only 11,000 miles per hour, making it easier for atmospheric gases to escape to space over time. This difference helps explain why Mars has such a thin atmosphere today compared to its thicker early atmosphere. On the other end of the spectrum, Jupiter's escape velocity exceeds 130,000 miles per hour, allowing it to hold on to even the lightest gases like hydrogen and helium that would quickly escape from smaller worlds. The formation of the solar system involved a complex dance of gravitational interactions that scattered objects throughout the cosmic neighborhood. During the early chaotic period known as the Late Heavy Bombardment, the giant planets migrated from their original positions, dramatically reshaping the architecture of the entire system. Jupiter may have moved inward toward the Sun before being pulled back outward by Saturn's gravity, a process that could have scattered the original asteroid belt and delivered water-rich objects to the inner planets. This grand tack migration model helps explain many puzzling features of our solar system, from the current distribution of asteroids to the presence of water on Earth and the unusual characteristics of the terrestrial planets' orbits. Some moons show evidence of past or present subsurface oceans through the patterns of cracks and ridges on their surfaces. The icy shells covering these hidden seas respond to tidal stresses by fracturing in distinctive ways, creating linear features that map the underlying ocean's influence on surface geology. Europa's linear ridges may form when tidal heating causes the subsurface ocean to bulge upward, cracking the overlying ice in predictable patterns. Similar features on Ganymede and Enceladus suggest that subsurface water may be more common in the outer solar system than once thought. These surface expressions of hidden oceans provide crucial clues about the depth, salinity, and dynamics of these buried seas without requiring direct drilling through potentially miles-thick ice shells. The solar wind creates different effects on planets depending on whether they have magnetic fields to deflect the charged particle stream. Earth's magnetic field acts like an invisible shield, deflecting most solar wind particles around our planet and channeling some toward the poles where they create beautiful aurora displays. Mars, lacking a strong global magnetic field, experiences direct interaction between the solar wind and its upper atmosphere, gradually stripping away atmospheric gases over geological time. Venus, despite having no magnetic field, is protected by its dense atmosphere, which creates an induced magnetic field that partially deflects the solar wind. These different interactions help explain why planets with similar sizes can have vastly different atmospheric evolution histories. The concept of planetary migration suggests that worlds can change their orbital distances over time through gravitational interactions. Computer simulations of the early solar system show that planets don't necessarily remain in the orbits where they formed, but can spiral inward or outward based on their interactions with the disk of gas and dust from which they condensed. This migration process may explain why we find hot Jupiters, gas giant planets orbiting extremely close to their stars in other solar systems. In our own system, Neptune may have formed closer to the Sun and migrated outward, capturing Pluto and other Kuiper Belt objects in gravitational resonances during its journey. Understanding planetary migration helps astronomers make sense of the diverse architectures observed in planetary systems throughout the galaxy. The day and night cycle experienced by different moons depends on whether they're tidally locked to their parent planets. Moons that always show the same face to their planet, like our own moon, experience day-night cycles based on their orbital periods rather than their rotation. This means that a day on the far side of our moon lasts about 29 Earth days, with 2 weeks of continuous sunlight, followed by 2 weeks of darkness. For moons orbiting closer to their planets, like those around Jupiter, the day-night cycle can be much shorter, sometimes lasting only hours. Additionally, moons can experience eclipses when they pass through their planet's shadow, creating complex lighting conditions that would be quite different from the simple day-night alternation we experience on Earth. The chemical composition of different regions in the solar system reflects the temperature conditions that existed during formation. Close to the young sun, where temperatures were high, only materials with high melting points could condense into solid form, leading to the rocky compositions of the inner planets. Farther out, where it was cool enough for water to freeze, the planets could incorporate large amounts of ice along with rock, allowing them to grow much larger and eventually capture thick atmospheres of hydrogen and helium. This temperature gradient also affected the composition of asteroids and comets, with objects forming in different regions carrying distinct chemical fingerprints that tell the story of where and when they formed in the evolving solar system. The gravitational influence of the giant planets extends far beyond their immediate neighborhoods, shaping the orbits of small bodies throughout the outer solar system. Neptune's gravity controls the orbits of many Kuiper Belt objects, including Pluto, through gravitational resonances that keep these distant worlds in stable configurations for millions of years. Jupiter's influence reaches even farther, affecting the orbital periods of comets and asteroids and occasionally flinging objects completely out of the solar system or redirecting them toward the inner planets. These gravitational shepherding effects create distinct populations of small bodies with different orbital characteristics, from the asteroid families in the main belt to the various dynamical classes of objects in the Kuiper Belt and scattered disk regions. The rotation periods of planets provide clues about their formation history and internal structure. Fast-spinning worlds like Jupiter and Saturn likely retained much of the angular momentum from the collapsing cloud of gas and dust that formed them, while slower rotators may have experienced major impacts that altered their spin rates. The relationship between a planet's rotation rate and its shape reveals information about internal density distribution, as faster-spinning worlds become more flattened at their poles. Unusual rotators like Venus and Uranus probably experienced catastrophic events that dramatically altered their original spin states, providing insights into the violent processes that shaped the early solar system. And now, as these gentle truths about our cosmic neighborhood settle into your awareness like starlight on calm water, let your thoughts drift even deeper into the restful embrace of sleep. We've wandered through the dynamic renewal of Saturn's rings and the gravitational music of orbital resonances, from the extended magnetosphere of Jupiter to the seasonal transformations that sweep across distant worlds over decades-long cycles. The solar system continues its ancient choreography around you as you rest, with shepherd moons sculpting ring gaps and Trojan asteroids following their eternal dance 60 degrees ahead and behind their planetary hosts. Hidden oceans pulse beneath icy shells, while solar wind streams past magnetic shields and through tenuous atmospheres, gradually reshaping worlds over geological time. Each planet spins at its own tempo, some racing through brief days, while others turn so slowly that their nights stretch for Earth years. Your body, made of elements forged in stellar furnaces and assembled through billions of years of cosmic evolution, rests now as part of this vast system of gravitational relationships and orbital mechanics. The same forces that guide comets on their elliptical journeys and maintain the delicate resonances between distant moons also hold the atoms of your being in their proper arrangements, creating the temporary but miraculous pattern that dreams and wonders about the universe. Let these cosmic rhythms carry you deeper into peaceful dreams. These patient worlds that have been dancing through space since the solar system's violent birth over 4 billion years ago. The planets will continue their stately procession through tomorrow and beyond, following paths carved by gravity and time. waiting to inspire awe in anyone who pauses to contemplate the serene majesty of our shared celestial home. The phases of our moon create a gentle rhythm that has guided life on Earth for billions of years. As our satellite waxes and wanes through its monthly cycle, it demonstrates the elegant dance between Earth, Moon, and Sun that creates these predictable patterns of light and shadow. During a new moon, our satellite sits between Earth and the Sun, its dark side facing us while the illuminated half remains hidden. As days pass, a thin crescent appears, growing steadily into a half moon, then a gibbous phase, and finally the full moon when Earth lies between the Sun and our lunar companion. This cycle then reverses, with the moon appearing to shrink back through gibbous and crescent phases until it disappears once more into the new moon phase. These phases have provided humanity with one of our most ancient calendars marking the passage of time with celestial precision that never fails. The density variations among solar system objects reveal fascinating stories about their formation and evolution. Saturn famously has such low density that it would float in water, a consequence of being composed primarily of hydrogen and helium gas, surrounding a relatively small rocky core. Earth, by contrast, is one of the densest objects in the solar system, due to its large iron core and rocky composition. Mercury, despite being the smallest planet, has a density almost as high as Earth's because of its proportionally enormous iron core, which may be the result of a massive impact that stripped away much of its rocky outer layers early in solar system history. These density differences help scientists understand not only how planets formed, but also what lies hidden deep within their interiors. From molten metal cores to layers of exotic ice phases that exist nowhere on Earth's surface. The auroras that dance across polar skies on Earth have counterparts on other worlds throughout the solar system. Jupiter's auroras are hundreds of times more powerful than Earth's, driven by the planet's incredibly strong magnetic field and the constant stream of charged particles ejected from volcanic activity on its moon Io. These Jovian light shows occur not only in visible light, but also in ultraviolet and radio wavelengths that create a complex electromagnetic symphony around the giant planet. Saturn's auroras are also magnificent, sometimes forming complete rings around the planet's poles and occasionally flickering in response to changes in the solar wind. Even planets without strong magnetic fields can experience aurora-like phenomena, as Mars shows faint atmospheric glows when solar particles interact directly with its thin atmosphere, creating delicate curtains of light in the Martian sky. The concept of Hill spheres defines the gravitational domain around each planet, where it can capture and hold on to moons. These invisible spheres of influence extend different distances from each world based on their mass and distance from the Sun. Earth's Hill sphere reaches about 930,000 miles from our planet, well beyond the Moon's orbit, explaining how our satellite remains gravitationally bound to us, rather than being pulled away by the Sun's much stronger overall gravity. Jupiter's Hill sphere is enormous, extending nearly 33 million miles from the giant planet and encompassing all of its many moons in a stable gravitational embrace. Understanding these zones of gravitational control helps explain why some planets can maintain large families of natural satellites, while others like Mercury and Venus, have none at all. The libration of the moon creates a gentle rocking motion that allows us to see slightly more than half of its surface over time. While the moon is tidally locked and always keeps the same face toward Earth, gravitational interactions cause it to wobble slightly in its orbit, revealing glimpses of the normally hidden edges of the lunar far side. This libration occurs in several forms, with the moon appearing to nod up and down due to its tilted orbit and rock back and forth due to its slightly elliptical path around Earth. Over the course of several years, these combined motions allow Earth-based observers to see about 59% of the moon's surface, even though only 50% is visible at any given time. This gentle cosmic rocking has been observed and measured for centuries, providing insights into the complex gravitational relationship between Earth and its closest celestial companion. The asteroid belt contains objects with dramatically different compositions, reflecting the diverse conditions that existed during solar system formation. While most asteroids are rocky or metallic, some are rich in carbon and organic compounds, preserving materials from the outer regions of the early solar nebula. These carbonaceous asteroids are among the darkest objects in the solar system, reflecting only a few % of the sunlight that hits them, making them difficult to observe, despite sometimes being quite large. Other asteroids are almost pure metal, likely the exposed cores of larger objects that were shattered by impacts early in solar system history. The diversity of asteroid compositions provides a sampling of materials from throughout the solar system's formation region, offering clues about the chemical evolution of our cosmic neighborhood. The precession of planetary orbits creates subtle long-term cycles that can affect climate and atmospheric conditions over thousands of years. Earth's orbit slowly changes shape over periods of about 100,000 years, alternating between more circular and more elliptical configurations that affect how much solar energy our planet receives during different seasons. Mars experiences even more dramatic orbital variations, with its eccentricity changing significantly over time and its axial tilt varying between 15 and 35 degrees. These Martian orbital cycles may help explain evidence for past climate changes on the red planet, including periods when liquid water could have existed more readily on its surface. Understanding these long-term orbital mechanics helps scientists predict how planetary climates might change over geological timescales. And so we reach the end of our gentle voyage through the solar system, where we've drifted from world to world like leaves carried on a cosmic breeze. We've witnessed Venus spinning backward in her own quiet rebellion, felt the whispered presence of Jupiter's gossamer rings, and marveled at the heart-shaped plains of distant Pluto. We've discovered hidden oceans beneath frozen shells, watched ancient storms rage for centuries, and learned how the very atoms of our being were forged in stellar furnaces and scattered across the void to eventually become part of this moment, this breath, this peaceful drift toward sleep. The solar system continues its eternal dance around you now, each world following its ancient path through the darkness. Tomorrow, when you wake, they will still be there, spinning and orbiting in their serene choreography, carrying their stories of ice and fire, of magnetic fields and auroras, of moons that sing to each other across the vacuum and comets that remember the birth of everything we know. Let these quiet worlds carry your dreams tonight, and may you rest as peacefully as Saturn's rings catching starlight, as gently as the moon's slow recession, as softly as cosmic dust settling on the shores of space. Sweet dreams, fellow traveler of the cosmos.